So hello and welcome everyone. So in this video we are going to solve the question delete nodes having greater value on right. So this question is kind of trickier, but it is very much easy to solve if you have solved a prerequisite question for this one. I'll be mentioning the prerequisite question for this and it will be very much easier for you guys to cope up with the question. So let's start. So first of all, let's try to understand what the question is trying to say. So in the question, it is given that you will be given a single linked list and you have to remove all the nodes in the list which have any node on their right hand side whose value is greater. And one thing that we should note is not just immediate right, but entire list on the right. So basically not the immediate right, we need to check all the elements which are present on the right hand side of the current node. And we have to delete that node. So let's try to understand with the help of the example given over here. So I have taken the same example which is given to us in the question. So in this, the n is equal to 8. That means 8 nodes are there and we have to find out that which nodes need to be deleted. So basically you have to delete the node. Basically, let's say this is the ith node and you have to delete it if there is a value present on the right hand side. If any of the node on the right hand side is greater than the current node, delete the ith node. So let's find out which node can be deleted. So let's check one by one. 12. Do you see any node which is greater than 12 on the right hand side? Yes, 15 is there. So delete 12. Okay, so 12 will be deleted. So now 15. On right hand side of 15, I cannot see any node greater than 15. So we'll keep 15 in the output linked list. So 15 will be present. Now moving on forward with the next node, 10. On the right hand side of 10, I can see 11. So I'll be deleting 10. So now the next node will be 11. On the right hand side of 11, can you see any node greater than 11? No. So I'll be including 11 in the output linked list. So the next node is 5. On the right hand side of 5, do you see any node which is greater than 5? Yes, obviously 6 is greater than 5. So I'll be deleting 5. And 10 has been also deleted. So now moving on forward with 6. On right hand side of 6, do you see any node greater than 6? No. So I'll be including 6 in the output linked list. So moving on forward with 2, on the right hand side of 2, how many nodes are there? I can see only 3 and 3 is greater than 2. So I'll be deleting node number 2. And the last node, I cannot see anything present on the right hand side of 3. So 3 will be present in my output linked list. So this is your output linked list and you have to print this in the output. So you can observe in the question itself, the output is 15, 11 and 6 and 3. So this is the output which we need to print. I hope you got an idea what the question is trying to say. So now let's try to focus on what can be the brute force approach for this same. So now let's try to understand how we can solve this question in a brute force manner. So the brute force manner is very much simple. So what you will be doing, you will be one by one iterating over each and every node. Let's say this is your current node. So you'll be checking whether this node can be deleted or not. So how will you check whether it can be deleted? You will be iterating over its entire right hand side. And if you find any value greater than 12, then that means this node will be deleted. And I can see on the right hand side of 12, 15 is present, so I'll be deleting 12. So in this manner, you can find out which nodes will be deleted from the given linked list, and one by one, you can delete all the nodes which are supposed to be deleted. And at the end, you will be left with the nodes which will be printed in the output. So over here, the output will be 11, 6 and 3. So this is going to be your output. So what will be the time and space complexity of this approach? So if you focus for each and every node, what are you doing? You are iterating over its entire right hand side. That means you will be iterating n number of nodes for n number of nodes, right? So basically the time complexity of this approach will be somewhat equivalent to n square. And if I focus on the space complexity, what will be the space complexity? The space complexity will be constant because over here you will be not using any extra space that will be required, right? So the space complexity for this approach comes out to be constant. So now here is our task. Can we optimize this approach? So we need to focus whether we can optimize this approach or not. So that will be our optimal approach. So now let's discuss the optimal approach. In order to solve this question is kind of similar to the question leaders in an array. If you have already solved this question, then you will get an idea how to solve this question. So now let's try to focus how this question is similar to leaders in an array. So let's take an example. So what I will be doing, let's write down the example. So now this is our example. Let's try to find out what will be the output. So in order to solve this question, what I'll be doing, first of all, I'll be reversing this entire linked list. So I'll be applying the reverse algorithm to reverse the linked list, and that can be done in order of n time, right? So I'll be reversing it, and after reversing, the linked list will look like this: 4, 8, 7, 11, 9 and 10. This is our reverse linked list, right? So now on this reverse linked list, what I'll be doing, I will be finding which is the current maximum node, and whichever node is current maximum, only those nodes will be included in my output. So I'll be needing a variable that goes by the name maximum variable. So this is my maximum variable, and what will be the initial value of this maximum variable? If you focus on the output of each and every test case, you will observe that the last node, that is the head of our reversed linked list, will always be in the output, because we know that in the input linked list that the last node will not have any node present on the right hand side. So it justifies our test case. So it justifies our condition that this node cannot be deleted because it does not have any node on the right hand side and no comparison is required. So basically I'll be initializing this maximum variable with the head of this reverse linked list, and I'll be taking two more variables, that is current and previous. So I'll be initializing current with the next of head, and this is my head of the linked list, and this is my current, and I'll be needing a previous node as well, as we are going to delete the node in this linked list itself. So now let's try to iterate, and one by one I'll be finding whichever node is greater than maximum. I'll be including that node in the output linked list. So basically let me write down the condition. The condition is that if the current node is greater than maximum, then I'll be including it. That means do not delete that node. So I'll be including it in the final linked list. And if I see if the current node is lesser than maximum, then what I'll be doing, I will be deleting that node. So these are the tasks which we need to follow if this condition is satisfied. So now let's try to solve this test case. So right now I can see that current is pointing to 8 and previous is pointing to 4. So what I'll be doing, this current will be compared with maximum. So 8 is greater than 4. So what is this? This condition says that if current is greater than max, then I'll be including it in the linked list. So including means I will be updating the value of previous. So your previous will be now pointing to current and your current will be moving on ahead. But before that, what you need to do, you need to update your maximum variable as well, right? Because you found a value that is greater than your maximum, that is 8. So update the maximum. So now your maximum value is equivalent to 8 and your current is updated to the next of current. So your current is pointing to 7. So now let's compare the value of current with the maximum. So 7 is lesser than or greater than 8. I can see 7 is lesser than 8. So I need to delete this node. So how will you delete this node? So logically, if you want to delete this node, I will make this previous point to the next of current, and then you can just update the value of current to the next of current. So this is how you delete the node. So let me write down the condition of how you will delete the node. So basically, if you want to delete the node, just update the value of previous.next is equivalent to current.next. Okay, and if you want to include the node, then that means what you will be doing, you will be simply updating the value of previous to current node, and you need to change the value of maximum as well. So basically your max will be equivalent to current.data, right? So these are the steps which you need to follow on each and every condition, right? And at the end, what you need to do, every time you need to update the value of current to current.next. Basically you will be moving on ahead with the next node. So these are the things which you need to follow on each and every node. So now let's check for the current node. Now your current node is equivalent to 11. So 11 is greater than 8. So that means I will be including it. So including means update the previous to current, right? So your current will be, so your previous will be now pointing to current node. So previous is equivalent to current and your current will be updated. Like basically the maximum value will be updated. So here now maximum will be equivalent to 11. So moving on forward with the next node, so your current will be equivalent to 9. So compare 9 with maximum. So 9 is lesser than 11. So basically you need to delete this 9. So what you will be doing, you will be making this previous.next point to current.next, and logically 9 will be deleted, and now moving on forward with the next node. So updating the value of current to the next of current. So now moving on forward, so I can see current is 10. So update, let's check what is the situation over here. So 10 is lesser than 11. So that means I need to delete the current node. So what you will be doing, again you will be making the previous dot next. Currently your previous is pointing to 11. So previous dot next will be pointing to null node because the next of 10 is null, right? So now your previous dot next will be pointing to current dot next, that is null node. So 10 will be logically deleted. And now after deleting the value of 10, what you need to do? You need to update the value of current. So your current will be now pointing to the null node, right? And you have iterated over the entire linked list. And basically what is remaining in the linked list? I can see 4 is remaining, 8 is remaining, 11 and null. So this is the output linked list which you need to print in the output. So in this manner you can solve this question. But over here we need to handle a corner test case as well. So let's focus what will be the corner test case. So now after deleting the node, this is what we have in our hand, that is 4, 8, 11. Basically this is not your output. We need to reverse this linked list, right? Because at this step we already reversed the input linked list. So basically after reversing you will be getting 11, 8 and 4 and null. So this is your output linked list and you can print it in the output. So what are the steps of algorithm? So the first step was to reverse the linked list and the second step was to apply the algorithm of deleting the node. Basically the same algorithm which you will be applying in the question leaders in an array. So that same algorithm is applied over here on the linked list. And after applying that algorithm, you will be remaining with a new linked list and that will be the reverse of the output linked list. So you need to again reverse it and after reversing you will be getting the output linked list. So here we need to update one thing because there is one corner test case. So let's focus what is the corner test case. So basically this is algorithm and let me give an example. So let's say the linked list was 7, 6, 7 and 4. So over here let's try to apply the same algorithm. There will be a minor change which we need to keep in mind while writing down this algorithm. So I'll be mentioning it over here with the help of this example. So let's focus. So I need a maximum variable. So this is my maximum variable and it will be initialized with what? Basically the first step of algorithm is to reverse this linked list. So reverse it and what you will be getting? You will be getting 4, 7, 6 and 7. So after reversing, this is our reversed linked list. So now what you need to do? You need to initialize the maximum. Maximum will be initialized with the head of the reverse linked list. So your maximum will be 4 and we need now current and previous. So current will be the next of head. So your current is over here and your previous is pointing to head. So now let's try to apply the same algorithm. So I'll be comparing the value of current with maximum. So I can see current is 7 and what is the maximum? I can see maximum is lesser than current. So I'll be updating the value of maximum. So our maximum will be 7 and what I'll be doing, I'll be updating the value of previous. So previous will be now pointing to current node. And now moving on forward with the next node. So your next node will be equivalent to 6. So over here you can observe this is my new node. So let's compare with the maximum. So comparing 6 with maximum, I can see 6 is lesser than 7. So I need to delete this node. So what you need to do? You simply need to change the previous dot next point to current dot next, right? And logically this node will be deleted and will be not updating the value of previous. Previous will be still pointing to 7. So now let's move ahead with the next node. So your current will be now pointing to the next of current, that is 7. So over here is the catch. So now what is the condition? So I can see that current node is 7 and your maximum is also 7. So I can see that 7 is equivalent to 7. Basically your current is equivalent to maximum. So that means what you need to do, basically that node needs to be included in the output because that node is not going to be deleted, right? So I'll be including equals condition whenever I am updating the maximum. So whenever your current is equivalent to maximum, you need to include in the output linked list. So over here in this condition, current was greater than maximum, right? So over here you will be adding if current is greater than or equal to maximum, that means you need to include that linked list. Because if you find the output of this linked list, the output of this linked list will be 7, 7 and 4. Right? So if you delete this node, then the output will be wrong. So basically whenever your current and maximum are equal, then you need to include that node in the output. So now I have included that node. So basically your previous will be pointing to current. So your previous is pointing to current. And Now you will be updating the current value. So current is now pointing to maximum, and you have iterated over the entire linked list. So what you will be getting in the output? You will be getting 4, 7 and 7. And this is the reverse of the actual answer. So you will be reversing it again and you will be getting 7, 7 and 4 is the output. So this was the corner test case which you need to keep in mind while solving this question. I hope you got an idea on how to solve this question, right? So I'll be quickly mentioning the steps of algorithm so it will be easier for you guys to write down the code in whichever language you code, right? So here is the steps of the algorithm. So the first step is to reverse the linked list. Reverse the linked list. What is the next step? Apply the same algorithm. Apply leaders in an array algorithm. Apply this algorithm on the reversed linked list, and at the end whatever is remaining in the linked list, again reverse the linked list and just print the output. So this is the entire algorithm. So now what will be the time and space complexity? Let's analyze. So over here on reversing the linked list, it will take order of n, and this leaders in an array algorithm is also order of n. Basically you will be iterating over the entire linked list, and again you will be reversing, and at the end you will be printing the output. It will be constant, right? So the overall time complexity of this approach comes out to be 3n, or you can call it as order of n. And what about the space complexity? The space complexity is constant over here. So this is your time and space complexity for this one. So now let's write down the code for the same and get it submitted. So over here I'll be writing down the code in Java, but you can write down the code in other languages as well. Just go through the algorithm. So first of all, what I'll be doing, I need to reverse the linked list. So I'll be writing down the steps of algorithm. So I'll be creating a function reverse that will be reversing the linked list, and it will be returning me the head of the new linked list. So I'll be updating it over here. And now applying the algorithm of leaders in an array. So I need a maximum variable, and maximum will be what? So first of all, maximum will be whatever is the value of the head node. I'll be putting it inside my maximum variable, and let's change the name of the maximum as maximum val. Okay. So now what do we need? We need the current node. Current will be pointing to the next of head, right? And what will be the previous node? So previous will be pointing to the head node. So now a simple iteration, while the current is not equal to null, I'll be keep on iterating over the entire linked list. So now I need to check two conditions, whether I need to delete or not. So let's write down, if the current node data is greater than or equal to maximum, that means that node needs to be included in the output. So if I include that node in the output, I simply need to update the value of previous. Else if, or you can put only else condition, that means if current data is lesser than maximum value, then that means that node need to be deleted, right? So if the current value is lesser than maximum, we need to delete that node. So basically you can write down in the else part. Else what you need to do, deleting means updating the previous.next. Previous.next will be equal to current.next. And over here you can observe, I'll be updating the value of maximum. So over here you need to update the value of max val as well. So that will be current.data. And at the end you simply need to iterate over the next node, right? So jumping the current to the current.next. So after iterating over the entire linked list, we again need to reverse whatever linked list we have in our end, right? So I'll be reversing the current linked list again, and you can return the head of the linked list. Or what you can do, you can write down the return statement over here itself, right? And I hope everyone knows how to reverse a linked list in order of n time, right? If you don't know that algorithm, I would highly recommend just go through that algorithm quickly. So node, and this will be your head node. So I need current node. Current will be equivalent to head, and previous will be initially equivalent to null, and temp will be initially equivalent to null. So I'll be iterating while current is not equal to null. So what I'll be doing, temp will be equivalent to current next, and current dot next will be equivalent to previous, and previous will be equivalent to current, and at the end current will be equivalent to temp, and at the end you need simply return the previous node. So this is the entire implementation, and let's try to compile and run. And the compilation is successfully done. So let's try to submit and let's see the acceptance. And we can see that the problem has been successfully submitted. I hope you got an idea on how to solve this question. So that was it for in this video. I'll see you in the next video. Thank you for watching, and do hit the like button and share it with your friends. Thank you.